Hey everybody, welcome to this week's lab. This is O4. We're talking about double slit, interference, and diffraction. This is one of the most famous experimental results in physics, and we get to do it in our lab. And unfortunately, you don't get to actually do it. You have to sort of follow along with the demo that Sean has and the lecture that I'm going to give on it. But hopefully I can do some justice to the fact that this is one of the most incredible physics experiments in history and changed the way that we look at light. Okay, so let's go ahead and get into it. For this lab, go ahead and watch this video. Watch Sean's video that showcases the procedure. He also talks about the theory of it as well if you're interested and need some more. There's also a ton of great videos online about it from various different sources like Khan Academy and stuff like that if you're interested in learning more. But then, so yeah, go ahead and watch those videos and then, use the data sheet, follow through the lab as best you can, and hopefully you'll gain an appreciation for how incredible this lab is. All right. So the first thing we need to talk about is waves. Now, what is a wave? How have we experienced waves in our lives? So a wave is pretty much anything that fluctuates or that oscillates, right? And so a really common example would be water. There's waves in the ocean, there's waves in a pool if you're in there like pushing the water around and stuff. But you can imagine something waving. So imagine this is a water wave here, right? Now this is really nice. Like the waves in the ocean usually curl over and fall, and those are a little bit more complicated, but we're talking about a nice simple sinusoidal wave. All right, so we could pretend this is water, or this could be sound, or anything else that waves really. What happens if I add another wave going over it at the same time? Can anybody guess? If I had another wave that comes in like this, what would the net result of those two waves added together look like? So these two waves, let's see, I'm gonna draw it like this. So if I have a wave that's like this, right? And I'm gonna add that to a wave that also looks about the same. You can see that the peaks of the wave line up, and the peaks line up, and the troughs also line up. So when I add these up, what does this equal? So this equals a wave that looks like this. It would be a really high spike and then a low trough, and then a high spike and a low trough. So what that means is like the peak and this peak, since they lined up together, they both added up and made a peak that's twice as big, and same over here with this peak. And then these troughs or valleys lined up, and they added up to give me a really low valley down here. So that's sort of one way that waves can add. We call this constructive interference, okay? That means that the high parts of the wave are adding together to get bigger, and the low parts of the wave are adding together to get bigger on the other side. But there's another way we could add these up. What if my second wave instead looked like this? So similar shaped wave, just it's offset a little bit. So I'm gonna say it starts here and it goes down and goes up and goes down and back up. Now you can see that there's a peak lined up with the valley, and so basically that's what happened here is we got our peaks lined up with valleys and our valleys lined up with peaks. And what this ends up giving you is nothing, right? So this ends up, every point on here cancels out with the other wave because this one's positive, this one's negative, this one's positive, this one's negative. When you add them up, they cancel out and give you nothing left over. That's called destructive interference. That's where the waves interfere in such a way that they cancel each other out. And then, as you might imagine, you can get anything in between here. If this wave was shifted over a little bit, like maybe this peak actually happened like right here instead, you can get some other funky wave where it's some combination of these two. Maybe it's a little bit smaller in places, a little bit bigger in places. And it can get really complicated, but we don't need to go into that. Just know that waves can add up and get bigger together, or they can cancel each other out. That is the fundamental basis for how the double slit experiment works. Okay, so that's a little introduction to waves. Now, what is light? Is light a wave? Is light a particle? You've probably heard this topic come up before, and if you haven't, it's a really interesting one. So for a long time, people assumed, like really famous scientists like Newton even, assumed that light was made up of little tiny particles. So if I turned on a flashlight right here, we'll call this a flashlight, that when it was shining its light out, what it was really doing was sending out a beam of a bunch of little particles called photons, all moving in one direction together. Okay, so that's the particle treatment of light. Now, along comes Thomas Young with his experiment, the double slit experiment, and he showed that light actually behaves as a wave. And then, fast forward a little bit further, quantum mechanics comes up, and they say, well, actually, light is a particle and a wave. So that's sort of the fast-forwarded result, is that we treat light as being a particle and a wave, and that's called wave-particle duality. And it comes up in a lot of interesting ways. So let me back up and talk a little bit about how the double slit experiment shows us that. So let's imagine you have a flashlight, just like I had before, like something like this, right? This is my flashlight, okay? And it's shining photons, light waves, I don't really know yet, out. And I'm gonna put two slits in front of it, and then this is going to be my a screen back here. This is where the photons or the waves can land. Now, what would Newton say, what would you say that the pattern of light on this background would be after shining a flashlight through two slits? You'd probably expect something like this: a really bright spot right here, and a really bright spot right here, right? Because there's two holes. Some of the light goes through the top hole, some of the light goes through the bottom hole, and you get two light spots. Actually, let me say bright to make it less confusing. So you might expect two bright spots like that. And you'd be right if these were, say, your hole in the size of your hand like this, and you were shining a flashlight through it. You know, you put your hands up like that, shine a flashlight through it, you would see two bright spots, and that's it, and not much brightness anywhere else. But something gets really interesting when you start reducing the size of these slits. And now the reason that Newton would say this is because his idea of light was with photons. And so his theory was that of all the photons coming out of this flashlight, about half of the photons would pass through this slit, about half of the photons would pass through this slit, and of course you end up with two bright spots where each set of the photons were landing. However, when you do this experiment with slits that are much smaller on the scale of, say, 0.5 millimeter, 1/4 millimeter, so we'll call it, so the slit width we're making really small now. So I'm going to leave them drawn this size, but just think about, we're reducing how wide these slits are in such a way that matches a characteristic of our flashlight, which I'll mention in a bit. Now, what you actually see on the other side is not two bright spots like that, like you might expect. You see something that looks like this. Bright spot, bright spot, bright spot, and then bright spots, bright spots, bright spots going outward like that. Now, this is not a very scientific way to draw this, so instead, I'm going to draw an intensity graph for the light along here. So, what the intensity graph actually looks like, so keep in mind this is the middle here. The intensity graph for a double slit looks something like this. That keeps going, and then let's see if I can draw this better on this side. It should be symmetrical, but my drawing is not the best. Okay, so this is what you see. And keep in mind that this is intensity right here, which means that a peak in intensity, a big bump like this, means a bright spot. A small bump like this means 0 intensity. So this is actually what you see when you shine light through two slits. You get a pattern like this, which is very strange if you think about it. You get a bright spot right in the middle between the two. You get two more bright spots on the other side of that, with a dark spot in between, and then it keeps going like that outward. Dark spot, light spot, dark spot, light spot, all the way out. And you start getting less and less bright as you go further out. But at least the first few are all pretty much the same brightness there for this double slit experiment. How does that happen? That's a very strange result. So that's what Thomas Young showed in his experiment, that actually light does this. And that's what we're going to see today in this lab, or you'll see in the graphs and the output results. And it is a really fun lab to do on your own, so I apologize that you're not getting the chance to do that. But hopefully you can understand how crazy it is that a flashlight, or we usually use a laser at this point, that a laser shining light through two slits produces a bright and dark spot pattern like this. It's incredible. Okay, so how do we treat this? How did scientists explain this? Because clearly this doesn't make sense if you're thinking about photons passing through each individual slit like this. That's where they came up with the idea of light as a wave. Now, to explain how light as a wave works, we're going to think about it like this. I'm going to reduce this down to a laser, make it a little bit smaller. So when this laser sends light out, we've been thinking of light as a straight line that moves in the direction of light. But when you treat it as a wave, what you're really doing is you're saying it has wave fronts like this that move out in the direction of light. Now, what's actually waving here, as opposed to compare and contrast with the water waves that we talked about earlier, where that's literally the water molecules going up and down in space, these, where I've drawn lines, correspond to peaks, and where I haven't drawn lines, they correspond to troughs of an electric field. Really, it's an electric field and a magnetic field tied together, but we don't need to get into that. Typically, it's represented by just the electric field, because the electric field strength is a bit stronger than the magnetic field. So, we can talk about this without even needing to know much about how the electromagnetic interaction works for a light wave. We can just say that the thing that's waving here is the electric field. There's an oscillating electric field and it moves through space. That's light. The interesting thing is that when a wave like this hits a slit, so say this moves out, and remember here we hit these two slits individually, but if the size of this slit is just right, and what we mean by just right is it's on the order of the wavelength of this light. If this slit size is on the order of the wavelength of this light, the light, when it comes out of it, will re-emit like it's a new source. Okay, so this slit gets treated as its own laser. So remember, when this laser, so if I back this drawing up just a little bit, we see my laser here. It actually starts out like this, and these waves kind of move out like that. When it gets to this slit, it's going to re-emit the same way it came out of here. So it's going to start small again, like that, and it's going to go like this. Now let me make some room over here, because you can probably see what's going to happen here is that when the same thing happens on this side, you get these wave patterns. Now I'm going to keep drawing this out. It's going to get a little bit messy. All right. Okay, it did get a little bit messy there, but hopefully you can see that, remember we said that these lines that I drew were the peaks? Wherever the peaks touch, you get a much higher electric field, and wherever the troughs touch, you get much less magnetic field or electric field. So this is how these two waves interfere the same way two water waves would, and there's actually some cool videos of that online. Maybe I'll link one in there, but if not, just take a look at it. Go ahead and Google it, and it'll show. You'll see that as the water waves move out and their peaks cross, you actually get a higher peak, and you get lower troughs, and it makes this interference pattern. And actually, when this all this craziness with these wave fronts here works out, you get that pattern that I had drawn up here, which was something like this, remember? Let's see. Down like that, round that out a little bit. You end up getting an intensity pattern like that. So this is how we explain this phenomena with waves. Now, your book walks through the actual mathematics of it, and shows an equation. Now, I'm not going to go through the derivation of the equation, but I'd like to talk about it at least. So let me remove some of this chaos from here, and I'll redraw my intensity pattern. All right. Okay. Make that a little bit smaller. There we go. Now your book has a nicer drawing of this, but I think this represents it. So we have some parameters in here. Now I'm going to go ahead and refer to my lab manual here. The distance from and let me just move some of this because this is a little bit noisy. Just remember that the waves are still coming in like that. All right, so some of the parameters we have in our lab manual, the distance from the slit screen to the measurement screen right here, this distance, we're calling this L. And then we've got the distance between the two slits right here. This is our distance D. And then the slit width itself is going to be A, and we'll cover that in a sec. Let's see. And then, of course, the wavelength of the incoming light is going to be lambda. And remember, wavelength is related to the frequency of the light, and it's also it's synonymous with color. The color is a less quantitative way to talk about it, but wavelength and color are tied together. So red light is 600 to 700 nanometers in wavelength. So you can think about it that way if it helps. Okay, so this equation relates the wavelength of the incoming light and the distance from the slits to the screen and the distance between the two slits and the distance between each of the peaks. Now, I want you to keep in mind that what we are doing in this lab is we're taking this phenomena, this incredible phenomena, and we're just going to play with it a little bit. And what we're going to actually use it for, we're going to use the data we take to compute the wavelength of our laser and see if we got it right. Now, I want to reiterate, I want you to keep in mind that this experiment was not originally about computing the wavelength of light. I don't want you to come away from this thinking that the double slit experiment is used as a fancy way to compute the wavelength. We're doing that as an exercise to play around with how this whole system works, but really the incredible thing here is that light behaves as a wave and as a particle, and if you treat it as a wave coming through here, you can actually build a mathematical model that predicts this behavior we see in real life. Okay, and this behavior right here, this is the weirdness, this is the cool part about this whole experiment, and it's actually a really famous part of physics as well. So, we're going to use our results to compute the wavelength, but that's not really the core fundamental punchline of this whole experiment. Okay, keep that in mind. So, we are able to derive, okay, we have to label our peaks first. So, this peak, first notice that on either side of this center line, it's symmetrical. And so the way that we've decided to label these is with just numbers. So we would call this peak, peak 0, and then this peak, peak 1, this peak, peak 2, and so on and so forth. Now because it's symmetrical, we call this one peak 1 also. So there's two peak 1s, one on either side. There's only one peak 0, and so we use peak number to be m. So this is the m equals 0 peak right here. This is the m equals 1 peak on the bottom side, and this is the m equals 1 peak on the top side. So that makes this one. This is the m equals 2 peak down here. This is the m equals 2 peak up here. Okay, so one of the questions we can ask is, how far is the m equals 1 peak from the m equals 0 peak? Or how far is the m equals 2 peak from the m equals 0 peak? And remember, because it's symmetric, the distance from m1 to m0 is the same as the distance from this m1 to m0 because of the symmetry. My drawing is not perfect, but if you believe that in real life it is a little bit more perfect, you'll find something like that. So our lab manual derives the equation for ym, and so we call ym the distance from the center of peak 0 to the center of peak m. So this would be, this distance I've just drawn is y1. This distance right here, that's y2. And just to draw them in over here, this is also y1. And this is also y2. And then in general, the distance from the center line to any peak m is ym. So this is some peak m equals m, something like that. Okay, the equation for ym is this. Ym equals lambda L over D times m. So that's the equation we're going to be using in today's lab. Now, I'm going to leave the rest of this from the lab manual, but I wanted to talk about how the peaks are numbered and how we relate this equation. Now, this equation predicts the distance of each bright peak starting from this 0 point. Okay, so you're going to have to use that. Now, briefly, this is the second part of the experiment. The first part of the experiment is the single slit. Now, let's talk about the single slit. Just briefly, so I don't give you guys a super long video again. Okay, the single slit is probably, like you guessed, it might be. It is the same thing, except there's only one slit, right here. Now, just to review, if you were Newton and you only thought that that light behaved as particles, what would you expect? You'd expect one bright spot right here and no other light anywhere else. However, this is not the case. And we actually find that the light spreads out. And this is called diffraction. This time, so Newton was close on this one because what you actually see is something like this. And remember, this is when our slit width is appropriately sized for the wavelength. I'll just go ahead and draw in my waves again. So we're going to use that in a sec. When the slit width is appropriately sized for the wavelength, you actually end up seeing something like this. Draw my center line. You get one big peak right here, and then some smaller peaks, smaller, 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 and smaller. Okay, this is what you end up seeing. Remember, this is our intensity. So you see one really bright spot here, and then two less bright spots on either side, two even less bright spots on either side of that, and so on and so forth, just off to infinity. Keep in mind that these troughs here are still dark spots, so it's really bright spot, little less bright spots, another dark spot, and so on. So, how does this work? Why does this work? Well, it turns out that for the same reason as before, how the light spreads out when it hits a point like this and re-emanates, we can actually talk about how the light that comes from the bottom of the slit, the light that enters at the bottom of the slit, takes longer to get to a certain point over here than light that came from the top of the slit. And that means that the waves, when they line up over here, remember how we drew the waves that if they lined up, they got bigger, and if they didn't line up, they canceled each other out? Well, it turns out that let's say that this is a dark spot, okay? So that means that the wave that came from here is exactly out of phase, that's what we call it, with the wave that came from here, and so they cancel each other out. For a bright spot, the waves are actually in phase again. So you can imagine right here at the center, the waves are, we got waves coming in from here and from here, and this one looks something like that, say. This one lines up exactly with it. See the peaks line up. Then we'll say that this is a dark spot, so maybe our peaks line up exactly opposite. Let's see. Like that. Oh, wait. Then maybe there's another spot up here where it's gotten so far out of sync that it actually gets back in sync, and you see that the waves line up again like that. Okay, and that gives us this constructive interference, destructive interference in between. And that is all. Oh, and then the last thing I'll say about this one is that we label the peaks the same way. So this is the m equals 0 peak at the center. This is m equals 0. This is m equals 1. M equals 1 down here. This would be m equals 2, even though it's small. M equals 2. And dot, 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 dot. Okay, now the equation for this one is a little bit different. Remember the other equation depended on d, but we don't have a d here. Instead, what we have is a, which is the slit width here. Now our lab manual calculates the equation for ym for us to be this. Boom. Good. Okay, so we can see this is another linear equation. Remember, it's almost the same as the last one. For the double slit, it didn't have this part, and the bottom was D. So let me just go ahead and put that up here. So this is the single slit. This is the double slit. So these are the two main equations we're going to use in today's lab. Okay, so what are we going to do with them? Just briefly, I'm going to talk about what we're going to do with them. We have gone ahead and in the lab manual, in the data sheet, you'll find values for ym for the single slit and values for ym for the double slit. We did one experiment with the single slit and 2 experiments with the double slit. There is a third double slit experiment in the end of the lab manual, but we're going to go ahead and skip that one. Just because our schedule's already been kind of thrown off a little bit, and I think that 2 does it justice already without really being in the lab. Okay, so what we're gonna do, we've calculated the values of ym, and now since I wanted to clear things up a little bit, and so since the lab has you actually measure this pattern on the screen with a tool that gives you the distance between these peaks on the screen. But since you don't get to see that part, I've gone ahead and just eliminated the measurements of the distances on the screen because you don't actually need them. All you need are the ym measurements. So if you believe me that I took my ym measurements correctly, which I did double check them and they look good, then that's all you'll find in the data sheet is just the ym measurements. So you're going to use these ym measurements. You're going to make a plot of ym versus this value m. So you're going to end up making a plot like this, ym versus m. And then what will that tell you? The slope of these plots will be, for the single slit experiment, the slope will be lambda L over A, and the slope of the plot for the double slit experiment will be lambda L over D. So we can expect for both experiments we'll get some sort of a straight line, and then we can go ahead and take the slope, whatever Excel gives us for the slope, and we know that the slope for single slit is equal to this. The slope for the double slit is equal to this, and we can work that backwards to find lambda, because we know L, we know D, or we know L and we know A. So that's the procedure. That is the analysis that I just talked about, is creating the slopes of the plots and doing this. And I'll try to write up a little thing on Canvas for that. But with that, that's all I got for you. Good luck on this. Please feel free to email me with any questions.